Let's take a look at the circuit here. We have the circuit on the left side here, top left, and we want to calculate a couple things. We want to calculate the inductor current, the voltage across the capacitor, and the voltage across the resistor at time t0 plus, so t greater than 0 in this case. And we wanted to calculate the changes in the current across the inductor, the changes to the voltage across the capacitor, as well as the resistor at that point in time. And we also want to look at the inductor current, the voltage across the capacitor, and the voltage across the resistor at time equals infinity. So we're looking at essentially in this problem, our initial and final stages, or initial final conditions and values. So that's what we're trying to solve in this problem. You see we have resistors, capacitors, and inductors. So this is an RLC circuit, and it's a second order circuit. Okay, so just like we did with first order circuits, we want to break this down into several stages. So we have one stage here. This is going to be the stage of t less than 0 or t0 minus. We have the second stage here, and this is going to be t right after 0, and it's going to be t0 plus. And then we have our third stage here, which we can technically call C. Call this guy C. And this is going to be our t equal to infinity. At t as it goes to infinity, so t of infinity. So that's going to be part C there. Alright, so these are the three different circuits. One thing I do want to note here is I didn't fully draw this last part here. So as t approaches infinity, our circuit's going to look like this. We're going to have the current source is going to be back in here. So we're going to have this current source here of 3 amps. Okay, so that's essentially what the equivalent circuit is going to be there. Alright, so we'll explain this here as we go. Let's start with the first section, first circuit, circuit A. Alright, so let's scroll up and start working this out. So for t less than 0, we know that our 3u of t is going to equal 0. Okay, and since this has reached steady state, and we know the properties of both the capacitor and the inductor, so the inductor is going to be replaced by a short circuit. So our inductor is going to be replaced by a short circuit. Our capacitor is going to be replaced by an open circuit. Okay, and that's essentially what we see here. Our inductor is going to be, here. So we have our inductor is a short circuit. Our capacitor is going to be an open circuit. Alright, and our 3u of t is going to be 0. So we come back up here, this is going to be 0. We get that circuit there. So this is the equivalent circuit for t0 minus. Okay, so from this figure we can figure out that our current across the inductor, I sub L, and this is at 0 minus, is going to equal 0. Our voltage across the resistor at 0 minus is going to also equal 0. And then our voltage across that capacitor, 0 minus, is going to equal minus 20 volts. Okay, so remember with the capacitors and inductors, the values cannot change abruptly, so they need some time to reach their values. Okay, so either rise or decrease. So that's what we have for the initial values for the current and voltages across those elements. Okay. And if we were going to take the derivatives of these guys, they will all be 0, because it has reached steady state at this point and nothing changes. Okay, so now let's look at the second stage. So we've solved for these guys. Let's look at the second stage, which is t greater than 0 or t0 plus. In this case, our 3u of t is just going to be 3. So we got 3 here. So 3u of t is just going to be 3 amps. All right. So if you look at this here, the inductor and the capacitor again cannot change abruptly. Now of course we're no longer in steady state, so we've got our capacitor in here and we got our inductor in here. They're not going to be open circuited or short circuited, so they're in there, so you have pretty much the entire circuit put together. A couple things we're going to do in solving using this to solve some of these values, especially the derivatives. We're going to add a voltage across this resistor. We're going to define node A and node B here, and then we'll move forward from those. But let's go ahead and come back to the this circuit here. Because the capacitor and the voltages, the capacitor voltage and the inductor current cannot change abruptly, then we can also say from previous. So IL at 0 plus is going to equal to IL 0 minus. Okay, and we said that was 0. Similarly, VC 0 plus is equal to VC 0 minus, which we said was 0. Excuse me, was minus 20 volts. Let's go ahead and fix that. Minus 20 volts. Okay. Now we're going to take the voltage across, define the voltage across the 4 ohm resistor here as V naught, as I mentioned, and we're going to apply KVL and KCL across this. Okay, so defining that as V naught, we're going to apply KVL and KCL, and we're going to call that V0. So if we look at node A at this circuit, let's say we take KCL at node A, we're going to get 3 amps equals, so the current going in is equal to the current going out, VR at 0 plus over the 2 ohms plus, in this case V0 as we defined it, 0 plus over the 4 ohms. Okay, so we got that equation here to work with, and then we can apply KVL next. Okay, we can apply KVL next, and if we do that, let's go ahead and do KVL to the middle mesh. So if I do KVL here, across here, the middle mesh at middle mesh, I want to keep these all on the same screen here. We get minus VR, again we're in the 0 plus condition, plus V0, okay, plus VC. We're just essentially doing KVL across that loop. Alright, plus 20, all that should equal 0. So if all that equals 0, we just need to rearrange those equations. Okay, so based on this, let me scroll up and let's further simplify this. We know that VC 0 plus is going to equal to minus 20 from up here. VC0 plus is minus 20, so we can plug that in here. Essentially what that means is those guys are going to cancel. The 20 and the minus 20 are going to cancel, and then you can simplify this equation and you get VR 0 plus is equal to V0 0 plus state. Okay, and then from here we can further simplify. We can get VR 0 plus is equal to V0 0 plus is going to equal to 4 volts. Okay, so we come back up here. So this is what we're getting up here. Alright, so we can highlight this guy. So we've got these guys defined, and then we've got this guy defined. Alright, so let's go to the next part here. So we know that L dV dt, I'm gonna scroll up here. I'm gonna come up here. So we know L dIL over dt is equal to VL. So we can rewrite this as dIL of 0 plus over dt is equal to VL 0 plus over L. And now we can apply KVL at right mesh. Okay, so we come back here and we can apply a KVL across this mesh here, and from there we can get VL 0 plus equals VC plus 20. All this should be 0, and then we can rewrite this as I dIL 0 plus over dt equals 0. Okay, now we can do the same thing for CdVC over dt. So we'll come down here. So I'm gonna highlight that, and then we can do the same thing similarly. We know that CdVC over dt is equal to IC. So dVC over dt is equal to IC over the capacitor, and then we apply KCL at node B. Again, node B is going to be up here to get the current going in versus the current going out. So let's go back up here and rewrite this. So to get IC, so we're going to have to get IC. So that's going to give us V naught of 0 over the resistor value is equal to the current going out, which is IC plus IL. Okay, and then since V naught 0 plus is equal to 4, and we know IL 0 plus is 0, then IC is going to be 4 over 4, which is going to give us 1 amp. Okay, it's going to give us 1 amp. Then we can rewrite this here at dvc over dt is equal to IC over C, which equals 1 over 0.5, which gives us 2 volts per second. I'll highlight that as well. Okay, now I'm going to come up here to get dVR at this point in time. We want to apply KCL at node A. Alright, and if we do that, we can obtain the following equation. Okay, so it's going to be 3 is equal to VR over 2, okay, plus V naught over 4. So we're going to get, again, when we look at node A, here we got 3 is equal to VR over 2, plus V0 over 4. So let's write that. 3 equals VR over 2 plus V0 over 4. And we take the derivative of that. We get 0 equals 2 dVR 0 plus over dt plus dV0 at this time over dt. And then we could also apply KVL to the middle mesh. And we get minus VR plus VC plus 20 plus V naught equals 0. We take derivative, and that's going to give us, so if we take the derivative of this, it's going to give us the following. It's going to be minus dVR, okay, minus dVR over dt. Let's write that. Minus dVR over dt plus dVC over dt plus dV0 over dt. We can substitute what we know here, which is dVC of 0 plus over dt is just the 2 volts per second. Okay, from here, and if we do that, we get dVR over dt is equal to 2 plus dV naught over dt. Okay, and then further substituting this to the previous equation, so we have this guy up here and this guy here, and we can further simplify this. I'm going to scroll up. dVR over dt is equal to 2/3 volts per second. We'll save this guy. Okay, so we applied a couple KVLs and KCLs here to get the voltage across the resistor, the voltage across the capacitor, and now let's look at the change of the voltage across the resistor and the capacitor. Now let's look at DIR. Now let's say DIR 0 plus over dt. We know since VR is equal to 2IR, we can say our DIR over dt is equal to 1/2 dVR dt, which is really 1/2 times 2/3, where the 2/3 is coming from here. Okay, which gives us 1/3 amps per second. So that's another potential value to save. Okay, so that's the bulk of the computation is gonna come from this state here. Okay, the bulk of the computation is coming from here. All right, now let's look at as time approaches infinity, which is going to be coming from this final circuit here. All right, so as the circuit goes to infinity, as the time goes to infinity, this is going to reach steady state. So we're going to be steady state again. Okay, meaning this circuit, the last circuit's going to be equivalent to the first circuit, except now we have that the current source is going to be working. So we can do the current division in this case. So let's look at as t goes to infinity. We're going to do the current division on that circuit, and we'll find that I sub L at infinity is going to equal to 2 over 2 plus 4 times that 3 amp current, which is going to give us 1 amp. So that's one value there. And then our VR at infinity is just going to be 4 over 2 plus 4 times 3 amps. Again, this is amps here. Times 2. And this is going to give us 4 volts. We'll highlight that. And finally, our VC at infinity is just going to be minus 20 volts. A 2 there, minus 20 volts. And that's how we do the initial and final values of a circuit. Okay, so go back and review these steps, make sure I didn't make any mistakes, and that all the steps make sense. I went through the math fairly quickly, but double check the math here, make sure again I didn't make any mistakes. But I tried to highlight the blue as the potential results here for the problem statement. All right, so the key again for all these is making sure that you put these circuits in the proper you draw these circuits properly for the different stages, and then solve accordingly based on the equations given to you. All right, we'll stop here and we'll do another example